So Nick promised that we will relax today and have fun. It's actually not what's happening. So I have like so many things to tell you, and it's going to be like 10 different topics, and it's probably I try to make it like structured in a way that you can digest, but it's a lot of information. So yeah, but I hope it'll be fun. So okay, so let's start with some quick recap of what we saw this week, and then I'll kind of give you some kind of survey of a bunch of things that we didn't cover, like that have been happening in this area. Yeah, and the goal really is to maybe like make you comfortable like reading papers and stuff like that, and like so that when you read papers or hear talks in the conferences, you will like some of the things that will be mentioned you will have heard and have maybe put them in some kind of context. Okay, so right, so we had we started with this class P. It was like a mess. We didn't know what's going on, which problems are hard, which ones are easy, and so on. And now we can draw this nicer picture here where we have these three classes defined based on some famous score hard problem like SAT, 3-sum, APSP. So each one has its subclass of problems that are hard, and this lets us classify many of the problems in the previous slide. And so we saw a bunch, and there's many others we didn't see. And yeah, on Monday we talked about 3-sum. Tuesday we talked about APSP. We showed this equivalence with the negative triangle problem, and which then you can reduce to a lot of other problems. And in the last 2 days we were talking about SAT, and OV, and that stuff. So okay, so what else has been happening in this field? And I like to classify the research into 3 topics. So the first is like the obvious thing is like you just try to classify more and more problems. So you just you take a problem like the problems you guys are working on and stuff, or some classical problems that everyone knows, and you say, can I do better? And so in some cases we have lower bounds, sometimes we don't. So we try to prove higher lower bounds, or maybe come up with better algorithms. And that's kind of the obvious thing to do in this. And then, a lot of work is like that. But then there are other works that try to kind of boost the theory and go from like these hardness results that are worst case, exact time complexity in the classical like word drum model and stuff, and go to other settings like, let's say, quantum. Like, okay, what happens if now I have a quantum model, not like a classical model? What happens? Can I still do these fine-grained complexity results and so on? Or maybe average case, so you know that the problem is hard in the worst case. What happens in the average case? Or approximations and so on. So these kinds of things, they try to take like the hardness result and try to make it like more interesting, more robust, more meaningful. And that's kind of like natural. Like that's what happened with the classical complexity, right? We had the kind of NP hardness results in the 70s, and then people started asking average case, approximations, parameterized complexity, all these questions. So that's kind of what is naturally also happening in P. And that's like a second type of work. And the third type is like just investigating the foundation. So this whole theory is based on these conjectures. So people are asking, are these conjectures even true? They're trying to break them or prove them in some kind of ways, even though it's very hard to prove quadratic lower bounds, but try to prove them under certain assumptions and so on, or try to suggest other conjectures, better conjectures, try to find connections between the conjectures and so on. So this third kind of work is like it's not looking at the applications at the lower bound, but just looking at the conjectures themselves and trying to understand them. So yeah, so we'll not talk much about the first thing. That's kind of like, just like whatever problem you have, you can think about. The talk will mostly be about the second and the third types, and it'll be like 2 halves. So let's start with this, with the second part. And yeah, let's just go over all these kinds of things and try to say a few words about them. So in this talk, like I'll spend like at most 10 minutes about any topic. So we'll keep switching topics. So quantum. So what happens if you add quantum algorithms into the picture? Any comments on this? What do you think? So is that true or?
I'm guessing you just get quadratic speedups on like everything.
Yeah, that's kind of natural guess. So, and this, why is that?
You have Grover search, which all the problems we've been working on are abstract research problems.
Exactly. So there's this Grover search magic in quantum, which basically says you can like, if if there are n things you want to check, you can do it with square root n like checks quantumly. It's like some magic thing that gives a quadratic speedup pretty much for a lot of things. Like if you haven't seen this before, or you want to see like the formal thing, like there's this like theorem. It's like a version of Grover search. It's like a minimum finding. So there you have like n numbers that you don't know them. You can access them with some black box. And instead of running this black box n times to find the minimum number, you can run it only root n times with a quantum. And if you use this, you can, as he said, you can break the conjectures. So you can get these running times for problems. Like for SAT, you can get a square root speed up. For APSP, I don't think you can get a square root. You can just shave that factor.
What is a quantum algorithm?
Sorry?
What is a quantum algorithm?
What's a quantum? It's so. I mean, okay. There's a model of computation, quantum computers, in which you don't work with bits. You work with qubits, which are certain things that, if quantum mechanics is true, you can really realize them in the real world. So it's like a more powerful kind of computer that people are trying to build these days to actually realize. In theory, it's possible, but building it, engineering it is a bit challenging, has been. And then it lets you do certain things faster than you would do with a classical computer. But then the question for complexity theorists is, well, okay, how much faster and what things can you do faster? So I'm not gonna like define it. It's just if you haven't heard of it, like it's fine. It's just whatever, some kind of more powerful one. So yeah, so you get this square root speed up for a lot of things, and then you can say, but the reductions are still meaningful. Like if you reduce to some problem, and for that problem you also get a square root speed up, but then maybe you could have gotten a higher speed up. Like it's not. I mean, with quantum, sometimes we have more than quadratic speed up for some problems. But the fine-grained reductions are still meaningful. So then they would say that if you believe, like, let's say, quantum set, that 2 to the n over 2 is the best for SAT, then you would still get, like, let's say, linear lower bounds for a bunch of problems. And so there are some works that do that. So they make, like, quantum threesome, quantum APSP, and they show that the reductions are still meaningful. But actually, like, not all problems get a quadratic speed up. So Grover search is good for problems where you can parallelize. Like, for SATs, like, you just check everything. So instead of checking everything, you check, like, square root n time. But some problems, you need, like, a sequential algorithm that does something and then another thing. And then it's not clear how to use Grover search. And in fact, one of the big open questions in this context is for LCS, edit distance. These sequence alignment problems, can we get subquadratic time with the quantum? And the reason is, like, these quadratic algorithms, they're very sequential. Like, you're filling this one at a time, and Grover doesn't really help you here. So it's like, what I'm saying is, like, this, this hardness result from OV or from SAT, it's really good in the classical setting. It was tight lower bound. But then when you look in the quantum, it's not a tight lower bound. It's like like SAT is not really capturing the hardness of these problems.
Are there examples of like quantum reductions resulting in barriers the same way we saw with deterministic and even randomized? Is there some notion?
I don't think there's any like papers writing anything about it yet, but it is something that came up recently, so I think it makes a lot of sense. But
an area that is undiscovered yet, and a lot of papers can be published in it.
Yeah, sure, yes. Okay, that's it with the quantum. So back to classical. So the second thing is like beyond worst case, which could mean many things. Like we have hardness for some very worst case instances, what happens in natural instances, the instances that we may be interested in. And one question that was asked also earlier in the week, like what about average case complexity? So if you take a graph, a random graph, or if you take threesome, you take the numbers randomly from some range, what is the complexity of the problem? And so it seems like these problems, many of them should be hard. Then some problems will probably become easy, like triangle detection or something. If you have a random graph, then you have a triangle with high probability. But for threesome, you can choose the numbers in a certain range, and then you don't know if there's a threesome or not. And it seems hard, but we don't know how to prove it. Like we don't have a worst case to average case reduction. So some papers have actually made conjectures that are like planted threesome is hard. It's like saying that random threesome is hard. And they've used it to build some crypto and stuff like that.
Is there an average case version of SKH?
So yes.
I guess probably random formula that satisfy go, right? So that's
Yeah.
it's not good to just say like a random formula is there, because there's a more quite clear definition.
Yeah. So yeah, you can look at random formulas and ask.
But they're mostly unsatisfiable, so that's like a bad definition, right?
I think if you look at the threshold, then it's interesting. But like when you reduce to OV, I don't think you get random OV.
Yeah, your reductions will be average case also. But like if you have average formula,
Yeah. So getting these worst case to average case reductions for the decision problems is open and interesting. For counting problems, like if you say counting OV or counting threesome and so on, there are some good reductions that show that on the average case it's hard. Okay, so that's it about average case. Now back to worst case. Okay, what if we restrict the input? Like it's not worst case input, inputs from some family. And I've mentioned planar graphs before, so let me mention them again, right? So computing the diameter of a graph, you need quadratic time, even if the graph is sparse, has linear number of edges. And it has been very natural to ask, what if the graph is planar? So you can draw it on the plane. It's a very natural family of graphs that appears in many places. And and then, as I mentioned, there was a breakthrough getting subquadratic. So there was this breakthrough paper breaking the quadratic bound for that problem. But there's still a big gap. Like this was improved later. It's n to the 5/3 now, so 1.6. And there's no lower bound. So it's a very interesting question. But we do have some results along these lines. So you can talk about parameterized complexity in P. So parameterized complexity is like this area where you say, well, the input, it's like I have a hard problem, but then maybe the input has something easy about it. So there's some parameter that controls how easy is the input. Then I can get a complexity that depends on this parameter. So let me give you a couple examples of this. And so the point is, like, this has been done within P as well now. So for diameter, you can look at this parameter K, which is the tree width of the graph, which I'm not going to define it, but it's like some measure of how much the graph is like a tree. It's one of the most popular parameters in parameterized complexity. And you can study this question, like what is the complexity of diameter as a function of the tree width. And there's a simple algorithm that's like 2 to the of k log k times linear. So it's like linear algorithm with some exponential dependence on the tree width. So if the tree width is small, this is it's fast. And it turns out that you can show a Seth lower bound as a function of the tree width that says that you cannot get a sub-exponential dependence on the tree width. So if you have 2 to the little o of k, you need to have quadratic time. So it's like almost matching. And let me give you one more example, which is it's very cool. for a different problem now, for longest common subsequence, the one we saw yesterday. So you can look at many parameters for the problem, like the size of the first string, size of the second string. You look at the LCS itself, which is also kind of a parameter of the input. Like maybe if the LCS is small, maybe it becomes easier or harder. The alphabet size, some other kind of numbers that look at the pairs of letters in the sequence. The point is, there were these algorithms. I mean, this problem has been studied like for many, many decades. So people have analyzed it in various ways. And if you kind of simplify things, you get that this is an upper bound for the problem. These algorithms were all like known for many decades, and this running time depends on the parameter. So you gave me an input, I can look at the parameters and I figure out like what is the running time. And then Carl Brinkman and Marvin Kuhneman, they showed that this is really also a lower bound. So you cannot break this bound, no matter what the parameters are. For any parameters that are like polynomially related to one another, you can create instances that have those parameters and have this lower bound. It's like a very satisfying result in terms of parameterized complexity in P. Okay. Now back to planar graphs. So you might wonder, okay, like we don't know the diameter is hard, but do we know that anything is hard on planar graphs? Or it could be that everything is linear time. And so there are a couple of papers showing planar graph hardness results. Let me mention one example here. So it's a pretty nice problem. So I'll show it on a slide. So there is a lower bound for planar graph for the dynamic shortest path problem. So you have a graph, it's dynamic, edges come and go, but the graph is planar all the time. And you want to know the distance between any pair. So it's kind of like, if the road networks are planar, which they almost are, right? The query is just asking you to give me like the distance from point A to point B. And as we've been asking in dynamic graphs, you would like to get polylog and time for update and query for this problem. And there was a classical algorithm that got n to the 2/3 time for updates and queries. And can you get polylog? And it turns out that it's not possible. There's a square root n lower bound under APSP conjecture. So that's it with this kind of topic. So the last thing I want to talk about in this context is the approximations. Okay, so we've talked about this before. Now I want to give you like a kind of a survey of what else we know. Still, one of the biggest questions in the area is this question I also asked yesterday. Can we get a 1 plus epsilon approximation for LCS edit distance in near linear time? We don't know. There were breakthroughs recently getting to a constant approximation, but still not 1 plus epsilon. And we don't have lower bounds. Another big open question is in dynamic graphs, if you want maximum matching. So the problem in the exercise today, you will show a lower bound for the exact version for maximum matching in dynamic graphs. But what about 1 plus epsilon? Can you get that with polylog updates and queries? And it's a very active problem. People are really making a lot of progress recently on the algorithms. Okay, and the challenge is when you want to prove hardness of approximation is these gap amplification techniques, like we saw yesterday with this distributed PCP stuff. You go from saying like orthogonal versus like one place where they're not orthogonal to a problem where you have like 100 factor gap, like the inner product is 100 times more than something else. So what gap amplification techniques do we have? So I would say there's 3 kinds of techniques. First, there are these techniques for the diameter problem, which I mentioned when we saw this lower bound for diameter. It was 2 versus 3. So we had some constant gap, and it was kind of lucky and easy. But you can, there have been a lot of works on diameter, specifically increasing this gap from 2, 3, and so on, with some graph products. But in terms of general techniques, so we had this distributed PCP, which said that there's this max inner product or some kind of gap OV problem. And for that problem, we could show a gap with some polynomials and stuff. And then for that problem, we can reduce to a lot of other problems with gaps. OK, and that's nice. But what about problems that are here in these classes? So for some problems, we don't have Seth lower bounds. So what can we do? And there was some recent work showing hardness for problems that are at the intersection. So there are some problems that are hard under both conjectures, specifically this triangle type of problems, all-edge triangle, which is very similar to the triangle listing problem you saw on Monday by Nick. You saw a threesome hardness for this triangle listing. There's also an APSP hardness for that problem. So I want to tell you a bit about this work and the technique here. The point is there's now some kind of gap amplification for triangle type problems. So what does that even mean? Like, what's an approximate triangle problem? So I'll let you guess, but I mean, think about it, and I'll move on, and then well, you will see. So OK, so before telling you what is the gap, I mean, you will discover it now when I show you some kind of reduction. But let's start with the application. So what problem are we trying? Like, what is an interesting approximation problem to talk about? So APSP is a very interesting problem. So let's talk about approximate APSP. So how fast can you approximate APSP if you had just like want to be very fast, like linear time? So we know that exact is n cubed. If you want 1 plus epsilon approximation, you can kind of reduce to the unweighted case, and then it's n to the omega. And if you want like even faster, like quadratic time, you can get it with a 3 approximation. But you know, if omega is 2, then like even 1 plus epsilon is quadratic. So it's kind of not so open here. But this thing died. OK, but if you want even faster time, like linear time, and the number of edges of the graph, then what can you do? OK, so suppose the graph is kind of sparser, so you don't want to spend quadratic time. And these things. So we have to change the definition a little bit, because like APSP, if you just define it as you have to output all the n squared values, then of course you need quadratic time. But here's like a different definition in which maybe you can get something faster. So it's like a distance oracle type of question. So you process the graph in linear time, and then you get queries, and then you have to say what is the distance. It's like kind of like the Gomori-Hu thing. Like you just get a data structure fast. You'd like to get it fast, and then you get a query, and you have to say what is the distance. And you should be able to answer queries in sublinear time, like polylog time or constant. So OK, that's like the goal. And then the question is, what approximation factor can we get for this problem? OK, so for this problem, approximate APSP, there was a classical Torup-Zwick algorithm. How many of you have seen this or heard of it? It's very famous in these called these graph approximation algorithms. It's like, you know, you sample node, you build the balls around them, and that stuff. Like, it's a very classical thing. And they got this 2k minus 1 approximation in running time that is m times n to the 1 over k. So the point is, like, you want to be fast, like you want the running time to be m times n to the epsilon, like 1 over 10. So you choose the right k. And you can get the answers with approximation that depends on the k, so maybe a 20 approximation. So there's this kind of trade-off. But what about lower bounds? So I'm going to show you a simple reduction that shows that this is like the right thing, but only for very small approximations, like less than 2. And now this will motivate like the gap triangle problem that we will talk about. So, okay, so here's a reduction from triangle finding to this distance oracle problem. And specifically, we will reduce from this all-edge triangle. So for every edge, we want to say if it's in a triangle or not. This problem is hard under three-sum by the same reduction you saw by Nick on Monday. So how do you reduce this to distance problems? So you take your graph. You want to know if these edges are in triangles. So what you do is you delete them. And you create a new graph. And then you ask for the distances in this graph. So if I ask about the distance between a pair BC, so what do I get? Do you see the connection? Yeah, so the distance is 2. If the distance is 2 and the BC used to be an edge, then I know that BC was in a triangle. Okay, so either the distance is 2, or if it's not in a triangle, then the distance is larger, so it's at least 3. And so if I have this approximate distance oracle, then I would solve triangle. So if I could pre-process the graph in linear time, answer queries in constant time, right? I'm only making a number of queries that depends on the number of edges. So everything would be linear, and I would solve the triangle problem. So I got this hardness of 1.5 approximation. But in fact, this is even a better lower bound. It's even a 2 approximation lower bound because like it's a bipartite graph. So if you can't get there with 3 really. You have to do at least 4. But that's it. Like that's what we had. And like so you might hope that this same reduction would give you something higher. Okay, like maybe 100. So if there's a triangle, you'd have a 2-path. And if there's no triangle, you would not have 100 paths. Which one?
Is it 4 over 2?
Yeah.
Why it hasn't written 2?
No, I mean just like in the yes case it's 2, and the no case it's 4. Yeah, so. But yeah, it's a 2 minus epsilon approximation. So you'd hope that in the no case, like the distance would be 100. But unfortunately, this will not be the case because like what if this edge was in a cycle, in a short cycle in the graph? So here maybe this is like a 5 cycle. And so like, you don't know that there are no short cycles in the graph. So this leads us to the gap triangle problem that we want to talk about. In the yes case, there's a triangle. In the no case, there is no short cycle. So if we could assume that the graph has no 100 length cycles other than triangles, then this same reduction would have given us a factor 100. And yeah, but it's not clear that this is a hard problem. And this paper with this technique with Carl Bringman, Sarikhouri, and Orzamir, we showed some theorem that says that, yes, triangle detection is still hard even if the graph doesn't have many short cycles. And the result we showed is like an almost tight lower bound for any k. So showing that like you can't get like even 100 approximation you cannot get in linear time. So this Torup-Tvik thing is essentially the right thing up to the constant. And in a later paper with Nick, we improved the constant. So now it's just a factor of 2 away from Torup-Tvik. And there was some cool technique in this paper where, we look at you want to remove cycles from graphs. So what we did is we go back to the threesum. So right, we know that triangle is hard because of threesum. So you go back to threesum and you say, why are there cycles in my graph? And there are cycles because in threesum you can have these arithmetic progressions or some like let's say 100 numbers that kind of 50 of them sum to the other 50. It's like this additive structure in the instance. And so we've used some additive combinatorics to say that threesome is hard even when the instance doesn't have these structures. Some cool stuff. Okay. So that's the end of the approximation. And I just want to give you one slide on one interesting open question. So I said I will not talk about that part of like giving you some open questions, but I will have one slide about it. There's some nice question that came out of this cycle stuff. So it's about subgraph detection or listing or stuff. Right, subgraph isomorphism, you have a graph and you have some small pattern and you want to know if this pattern exists in the graph. And so the question is, when is this easy and when is it hard? For what patterns it's hard? If finding an edge is easy. Finding a two-path is also easy. Finding a triangle turns out that it's hard. So what is the thing? Okay. So a very natural conjecture is that the problem is easy, meaning linear time, if and only if the pattern is a forest. There are no cycles in the thing. So finding tree, and we know the upper bound to be true. So we know that if you have a forest, finding it in a graph, you can do it in linear time. But can we show also a lower bound? So show that if there is a cycle in the pattern, then it's not in linear time. And so we know this for triangles, and it was open for 4 cycles. So the next cycle, like 4 cycle. For a long time, this was like a super annoying problem in fine-grained complexity. And with this same paper that I discussed before, we actually showed this. So we showed a superlinear lower bound for 4 cycles, and in fact for all cycles. So it seems like we're almost there. But it's very annoying that we cannot really prove it. So we don't, like, the pattern you're looking for, it's arbitrary, complicated. It has some cycle somewhere, but it has other things. So somehow, if you try to show a reduction, you will see it just doesn't work. Like, it could be that something with a cycle is easier than just the cycle. So I encourage you to think about this problem. It's like proving it would be very pleasing because we would really have this dichotomy. So for what subgraphs the problem is easy, what is hard. But yeah, it requires some new ideas. Okay, so now we're at the last part of the talk. So we're switching topics completely now. So let's talk about the conjectures. So of course it would be really good to prove them, but even just proving consequences of them. So if you break SAT, then what happens? Like, can you get something very surprising? If you break threesome, like what happens? These kinds of things, we don't really have much. Something different is to say, well, let's use better conjectures. Let's find conjectures that are more believable, maybe, and then use them. And I'm going to mention a couple results along these lines. So you can look at the 3 conjectures and take the union. So say, here's a new conjecture, like at least one of them is true. Okay. I don't know which one, but like at least one of them. So to refute this conjecture, you have to refute all 3. So this conjecture is super safe. And let's try to use this to show lower bounds. And well, we did this, but it was very hard and there were very few problems. So there are problems that if you solve them faster, you break all 3 conjectures. So the lower bounds we have for them are super safe and great. Unfortunately, this has been almost 10 years, and we have very few cases like this. For most interesting problems, we can only show from 1 conjecture. 2 at best, but not 3. But yeah, the point is there are problems that are at the intersection. So I'm not going to define them, but they're about finding triangles in graphs where you have colors on the nodes and you want to find, like, are there like triangles from every triple of colors or something like this.
These problems capture any interesting tissue about the different conjectures?
I mean, I think so, but like it's not easy to describe it. Maybe, yeah. Like I think the reductions from them to these are very nice. Like these problems are just about triangles in colored graphs. So I think they're nice. Yeah. Okay, so that's like the first kind of thing you might try to do, and so on. And there's another kind of work that looked at Seth and tried to make it better. So what does that mean? So, right, so Seth, we have a lot of lower bounds under Seth. And what we could show is that for many of them, or for some of them, you could show lower bounds not under like Seth for SAT, for CNF SAT, but for circuit SAT. So let me explain the intuition here. So if you have, if I give you a black box, it has like n inputs. And the question is it satisfiable? So is there an assignment to the inputs that makes it output 1? If it's a black box, like you don't know anything about this, of course you're going to need 2 to the n. Right? There's no way you can beat 2 to the n. So like, SAT is hard, but the question is, in real life, I can't give you a black box. Like I have to give you something. So in KSAT, I'm giving you this formula, right? It's like OR of ANDs of a bunch of things. So it's like a very simple circuit, like depth 2 circuit of a specific form, of linear size even. And then the Seth says that, well, it's still hard. Like it's still like a black box. Like, okay, you can break this with some of these like 1 minus C over K things. But like you can't break it by much. But if I put like a more complicated circuit here, like a polynomial size circuit with like more layers and stuff, it becomes more believable that this is like a black box. Like if I just put like any algorithm, any computer here, it's like to break this, you kind of have to analyze the computer and figure out that if it's satisfiable or not. And this is something that is very difficult to do in general. And so that's what we did there. So we looked at circuit SAT for like circuits, pretty large family of circuits. And we showed that, perhaps surprisingly, you can still do the reductions for some problems, specifically for these LCS, sequence alignment problems. And this is kind of surprising because, for example, we cannot reduce to OV anymore. Like the reduction to OV really exploited the specific structure of KSAT. We look at the assignment here, assignment there, and this becomes like orthogonality. But when you reduce from an arbitrary circuit, it's like, you have to implement a lot of computation in the reduction. But the message from that work is that this LCS and stuff, they are very powerful, those problems. You can really encode a lot of things. And so what's the point of that? So first point, just intuitively, this is a safer conjecture, circuit SAT. But also, like, if you break circuit SAT, then you also break some kind of crypto assumptions, like with there's these one-way functions that people use and believe they are hard. You cannot implement them with a CNF, but you can implement them with circuits. So you would get some surprising things. And there is also some connection to circuit lower bounds. So this is a topic I'm not going to introduce properly, but like, proving that P different from NP is very difficult. So people are trying to prove, things that are even weaker than that and so on. And currently they're proving that some NX, some very large classes is not contained in very simple circuit classes. So, and they're trying to go forward. And so if you solve LCS faster because of this result, then you go like very, very, you make a lot of progress in circuit complexity. There's some connections showing that if you solve SAT faster for a certain class of circuits, you get circuit lower bounds for that class of circuits.
When you say breaks crypto, does that still happen if you have 2 to the power epsilon n, or do you
I think this is probably exaggerated. Yeah, it's like you break it a little bit. You break the belief that this is hard, but not. Yeah.
But the conjectures are for like different circuit families. Like do you have a circuit set do you have a circuit SE for various different classes of circuits, like DC or something? And then if you could have a reduction that was kind of mapping, I think that would be a barrier for, like let's say added distance to be solved, and you have added distance reduction to like DCC or circuit set, then that's kind of a barrier including any kind of, you can't use Ryan's method to let's say prove lower bound. And that would be a fine way of proving the barrier for like lower bound. solve the proof is low, but we must get like an incremental exponential in an algorithm for edit distance. Why? If you want to like get fast circuits and algorithms to get
No. Okay, yeah, no, the reductions only go in one direction. So we're only taking circuit sat and reducing to edit distance. So if you give me a faster algorithm for circuit sat, I don't know how to use it to solve edit distance faster. So it could be that there is a faster circuit sat algorithm, and nothing happens for edit distance. Yeah.
How much can you weaken the circuit sat while the third arrow in the one-way circuit algorithm still happens? For example, can you reduce from depth 3 or depth 4 circuits? Or constantly?
Yeah, I mean, in fact, like to get this breakthroughs in complexity or to make progress in the circuit lower bounds, it's enough to break sets. So if you break set for CNFs, you already get something interesting. But what you get is like, the next step of what people are trying to do. But if you break circuit sat, you make like 100 steps. Like you prove that NC1 and like large classes are not, or even NC. And so that's cool. Like this makes the lower bounds maybe a bit more believable. But there's also another cool consequence, which is about shaving log factors. Right? So I said you can shave 2 log factors from LCS. Now it turns out that if you shave like 100 log factors, or maybe even 10, you can already get really cool stuff. And the reason is that, well, this running time, like shaving like, for CNF sat, the current running time is like 2 to the n over something that's super poly. So for CNFs, we can shave something very substantial from 2 to the n. But if you talk about circuit sat, then we don't know. Like even getting this, even shaving like a small factor from 2 to the n is open. And in fact, this would already imply the breakthroughs in complexity. You don't have to break set, you just have to solve it a little bit faster. And so then if you go through the reductions from 2 to the n to n squared, and you say like, okay, if I shave a log factor here, like for OV or LCS, how does it translate? Well, it translates into a poly factor here. So if you solve LCS, you shave more log factors, then you shave this poly factor for circuit sat, and you get some breakthrough. So it's kind of cool. Like this is like very fine-grained reduction. And yeah, so that's great. We have it for some problems, but we don't have it for everything, like for diameter, and not all problems are able to encode circuits. So say for most problems, you're just working with CNFs. But when possible, showing that it is, then it's cool because you get better lower bounds, and also you talk about shaving logs. Okay, so that's it about like better conjectures. Now I want to talk about other conjectures. And so there has been a few other conjectures that we'll mention. But if we had like one more day for the workshop, I would have spent it on K-clique. Like this is my favorite like extra conjecture. So let me tell you about it. So K-clique, you have a graph, and you want to find K nodes that are a clique. So it's kind of like triangle. Triangle is like a 3-clique, and when K is larger, you have this K-clique problem. So how fast can you solve this problem? So n to the k is trivial. Does anyone see it better than n to the k? Yeah. Right. Right. So this reduction. You take your graph, and you generate for every k over 3 clique in your graph, you create a node. So you have this. You have your graph on n nodes. You create a huge graph on n to the k over 3 nodes, where every node in this graph is really like k over 3 clique. And then you define the edges in this graph. So you put an edge between 2 of these super nodes if all the edges like existed in the original graph. And then if you find a triangle in this graph, this huge graph, then it corresponds to a k-clique in the original graph. And then you can do matrix multiplication here to find the triangle. Okay, and that's the best we know for this problem, and well, we can conjecture that this is the best possible. But if you talk about weighted, so right for triangle, right, we had this n to the omega, but then we went to weighted, like negative weight or minimum weight, then we didn't have it. So it's the same thing here. If you talk about weighted clique, like min weight, then n to the k is still the best. You can shave this 2 to the square root log. So there's really like 3 conjectures here. So there's the conjecture that for weighted, you cannot beat n to the k. There's the conjecture that n to the omega k is the best. And then there's this combinatorial thing, which I'll talk about later. So don't worry about it for now. And the point is, like, the triangle was conjecturing these things for k equals 3, like for minimum triangle and stuff. But now we're saying it for all k. And notice, like, if we break triangle, then we break k clique because of this reduction. If you solve the, let's say, negative triangle in subcubic time, you break n to the k. But the other direction is not true. So there's been a lot of lower bounds under this conjecture. It's a very useful conjecture. So yeah, so I would put it as like a 4th conjecture here. So let's talk about connections. So what do we know about the connections between these conjectures? So we've already seen, like, triangle and APSP are equivalent. So I can write, instead of APSP, I can write min triangle or min 3 clique. And because of this reduction, I have this arrow. So that's like one connection. So in some sense, in some sense, these 2 conjectures are not really different. It's like just like a boosting of that same conjecture. Nice. Going in the other direction is we don't know. Like, we don't know how to reduce triangle to k clique in a tight way. And this is a general issue. Like this, also going from 2OV to KOV and stuff like that. This seems like a barrier. It would be great to show something like this. Okay, but so there is some connection I want to tell you. So let's look at OV, right? So you remember there was SAT and then there was OV, and we reduced to a lot of problems. And Seth gave us that OV is hard on log n dimensions. But as I said a few times, like, we don't really care about this so much. Like, even if it was n to the epsilon, the dimension, then it's still interesting for most problems in P. So let's look at the OV, like sometimes called medium dimension OV. So OV with dimension n to the epsilon. And for most problems in P, you can still use that conjecture. So perhaps the only exception we know is this distributed PCP that you saw yesterday with Nick. For that, they really used like the log n dimension. But in general, you don't need it. And yeah, there it's open. But then, okay, now I want to put the OV medium dimension there, and then I'm going to show you a cool result. So here's, okay, before, first, like, okay, what we would have liked is to unify things, right? To show that Seth implies everything. And yesterday you heard that this is difficult because of this non-deterministic barrier stuff. So you showed this thing for threesome with the verifier and stuff. And in the exercise you will see for APSP, which also then implies for min k clique, because like if you solve APSP, you also solve clique. Okay, but what else? And it turns out that this arrow is true. So if you solve OV faster, not OV on log n dimensions, but on n to the epsilon dimension, so you have to solve it like better, then you break minimum weight clique. That's a pretty cool unification. It says that this conjecture, this k-clique conjecture, it's like, you could have started with it and have classified almost everything that we know. Well, except for the threesome class. We don't know the reduction to threesome. It would be great to have one. But yeah, for most other things, it's enough. And so let me throw another conjecture at you. So there's this min plus convolution conjecture that actually unifies threesome and APSP. So like these two, like clique and convolution, are like, in some sense they are, they're hard problems. We don't know how to solve them, but they're like the easiest. Like, as I said in the first day, right? Like this picture means you shouldn't work on these problems. You should work on the conjectures. Well, then maybe you should start with the ones at the very top, like K-clique and the min plus convolution. Like they're only easier. So here's min plus convolution. It's very similar to convolution threesome, but you replace like the equality and stuff with the minimization. So the input are these two arrays. You get A and B, and you have to output C, which is defined as the convolution. So for K, you take the minimum I and take AI and BK minus I. So it's like the minimum over all these options you have to write there. And you can reduce it to threesome and to APSP. And both of these reductions you have seen in the class. It's just variants of reductions you have seen. The reduction to threesome is the same reduction from negative triangle to zero triangle. And the reduction to APSP is the same reduction from this convolution to zero triangle also. Like instead of writing an array, writing a matrix. But yeah, the conjecture is that we cannot get subquadratic time for this problem. And yeah, and there are some lower bounds under it. Okay. So here's like simplification of what's going on, right? So we have these conjectures, and now I'm saying, oh, there are a bunch of other conjectures. So really, yes, there's plenty of other conjectures that people have been looking at. But I would say okay, so let me try to make some kind of order. So we have like the primary conjectures. These are the red ones. These are like the more famous and central ones and so on. And then people have been introducing, like, because they want to prove more and more lower bounds and so on, they've been introducing these secondary conjectures. So these conjectures, well, they're more recent, usually less famous problems, less well studied. And they're also usually stronger forms of the primary. So like we usually have a reduction from the secondary to the primary. So in some sense, what this means is that you can think of K-clique as saying, a triangle or negative triangle is still hard, even if the graph has a certain special structure. Right? To refute K-clique, you have to solve triangle in this kind of graph. And this is a very special type of graph. Look at this graph. It's huge, but it originated from a small graph. So it's like a very compressible graph, very structured. Like, the edges are defined based on some kind of product condition. And this specific structure is really what makes these conjectures useful. So when you show reductions from K-clique, what you're really doing is, you want to reduce from triangle, but then you need to assume something about the input, that it's like compressible and nice. So you do that. And yeah, so I showed like a bunch of these secondary, but actually there aren't really that many if you think of them as following. So there's like three types of variants. So they're all like variants. And there's three main types of variants. So the first variant is talking about like the weights. So let's say threesome, right? One of the exercises was like, you can start with threesome on arbitrary numbers, and you can reduce the numbers to n cubed. You just hash everything down to n cubed, and this is just as hard. And then if you reduce the numbers further, like to n squared or below n squared, then there's some algorithm that's faster. But between n squared and n cubed, we don't know. And so there's a variant that says, well, even if I push it all the way to n squared, then it's still hard. And that's useful sometimes. When you do reductions, sometimes having smaller weights is useful. So this same kind of variant has been used for APSP and other conjectures. So that's like the first type. The second type is like going from k equals 3 to larger k. So for OV, actually, we have seen an example. We have some reductions from 2 OV and from from 3 OV. And for triangle and AP and clique, like this is what's happening here. And yeah, so we don't know. Like with Seth, we had Seth implies all K's, so that was clean. But with triangle, we don't know, so we have to make like a new conjecture for K. And same for threesome, like we have to make conjecture for K sum. So this is like the second variant. And the third variant is with the quantifiers. So there was a question in the exercise with this hitting set problem, which is like, it's like OV, but instead of asking, is there a pair, you ask, is there a vector here that is orthogonal to everybody? So it exists for all. Or for threesome, it's like you ask, is there an element that is in a threesome with everyone? Or with triangles, you ask, is there a node that is in a triangle with all the other nodes? Something like that. So you get problems that look exactly just as hard. Like all the algorithms we have for them, like, they don't solve them. Showing reductions is like we don't know. You change the quantifier, suddenly there's no reduction. Sometimes it's explained by NSET. Like this hitting set, it has some verifier. But yeah, so people have been like changing the quantifiers and saying, well, it's just as hard. So you get like new conjectures that way. Okay, so as a like very interesting open question that people are working on is, can we get unifications? Like, I mean, the thinking is like, the field is just starting in some sense. So let's just add conjectures and then try to kind of make order and unify things. And that's so making order now and reducing these variants to the primary conjectures is like super interesting. Or maybe we can find more variants that explain why we are not able to do it. Okay, so we're almost done. So what I have to end is like a philosophical discussion. So take a deep breath, and it won't be long, but it's going to be a bit philosophical. So this combinatorial business. How many of you have came across this combinatorial before? Okay, good, great. So I'm very happy that I'm talking about it. Like the point is like it's like something that people get upset about a lot, this combinatorial, especially with fine grained complexity, because we talk about it a lot, and people who are not in the field, they're like, what is this? And they get upset. And I wanted to like not let you leave here without telling you like how I view it. It's like the point is like to inform you of how we think of it, of this topic. So if what I say like will not make that much sense to you, but then in the future you want to go back, so you can look at this paper, recent paper, where we have some discussion that it's basically what I'm going to tell you now. So you can read it there. Okay, so what about combinatorial? And so let me start by saying like, usually I tell people like, you want to prove hardness, start with triangle detection. Triangle detection is like super simple, super easy. Try to reduce it to your problem, but assume that triangle requires cubic time. It's false. It's like we have subcubic algorithms. But like morally, it's like what you should start with, and then you try to like give better and more meaningful lower bounds. And the way we talk about this is with this notion of combinatorial. So we say combinatorially, there is no subcubic algorithm for triangle. So that means something. But okay, let's take a step back and see what's going on. Okay, so we have this triangle detection or Boolean matrix multiplication. So multiplication of 0, 1 matrices. Okay, so right, we can solve them in n cubed time. And if you want subcubic, then we have this, we can use Strassen or these fast matrix multiplication algorithms. We get n to the omega. And that's it. Like we don't have any other way of breaking cubic time other than these methods. So right, I'm calling all these methods Strassen and its improvements. So there are many, many papers, but they're all working in the same framework. So you take the matrix, you split it, you split both matrices, you find some formula to reduce the number of multiplications and so on, and you get a subcubic running time. And the formula, you have some subtractions, you're exploiting cancellations and stuff. So, and okay, so I mean, it's you know, we have some kind of things, or I don't know if I want to say issues with this algorithm, but there are certain things we would have liked to happen that don't happen with this algorithm. And so here's like a list of issues. And so maybe the more common things you might hear is that people say, well, it's not practical. There's like a lot of large constants and so on. It's not efficient in practice. Or so maybe other people say, well, it's not elegant, it's not simple, and so on. But the point is, like, I want to tell you, well, there's other things also. So there's these 4 things. And perhaps the most important from our perspective is the generalizability. So when you have a basic problem, very important problem, you want to solve it, you solve it, but then there's all these other generalizations you want to happen, and then that algorithm doesn't generalize, so you're looking for a new algorithm that maybe would generalize. So I'm in the next slide, I'll show you a bunch of generalizations that we would like to happen, and they don't happen with these algorithms. But let me mention the other things. So with the practice, these n to the omega things, they have huge constants and so on, especially the later improvements. So okay, like if you want to, you might want to find a different algorithm that would be more practical. Strassen itself is not that bad in practice, so it's not a very strong motivation here. It has some issues with practice in the way it uses the cache and stuff like that. But anyway, so that's one motivation that led to some of early works looking at combinatorial, but it's not really our motivation. The third one is like the elegance and simplicity. So, and that's probably the thinking behind the name combinatorial. So you're looking at triangle detection. Like it's just a super simple problem, like just finding a triangle in a graph. Like why should the best algorithm be this Strassen thing with the minuses and all that complicated stuff? And you look at what's happening in the algorithm, and you don't understand what's happening. Like you look at the intermediate values, and there's some crazy numbers, like they don't mean anything. So it's you would like to hope to have a more elegant or more understandable algorithm. And so I think that's part of the motivation. People started defining combinatorial in a way that's like you only take like subgraphs of your graph, or you take unions of neighborhoods and stuff that would be more understandable. And the last consideration is, well, we believe that omega is 2, or a lot of people believe. So triangle detection should be in like quadratic time. But this thing has been going for a long time. It's a very slow progress towards n squared and so on. So maybe if we find a different algorithm, then we would like immediately get to n squared. Like what I showed you with all pairs max flow. Like we were stuck for 60 years, then it was broken, and then within 2 years it was n squared. So maybe like finding a new idea here would lead to the n squared bound. So these are like motivations for seeking like different algorithms, which people have put the name combinatorial on. But really the most important for us is the generalization for fine-grained complexity. So let me explain what do I mean. So you can think of either like the Boolean matrix multiplication or the triangle. So the first generalization is weights. So if you add weights, right, you get the minimum triangle, negative triangle, or you get the min plus matrix multiplication. Strassen doesn't work, right? Maybe a different algorithm would work. That would be great, because then we would break APSP. Right? If we have an algorithm that generalizes, we break APSP. Right? A second motivation is reporting witnesses. So let's say triangles, right? You can decide if there's a triangle. But then if I want you to list all the triangles in the graph, you can't do that fast. So you cannot run. We don't have an algorithm that runs in subcubic time, and then it lists triangles like in constant time. Like when you do matrix multiplication, like the information on the triangle gets somehow lost. And so we would like an algorithm that would be subcubic and report triangles. And that would be great, because then it would refute a threesome. So if we have an algorithm that generalizes, we would solve this triangle listing problem that you saw on Monday, and we would refute threesome. Third generalization is online. So you get the one matrix, and the second matrix is coming one column at a time. If you break that, if you solve that in subcubic time, which Strassen doesn't do, then you refute this OMV from dynamic algorithm. And here's one more generalization to hypergraphs. So if you want to find cliques and hypergraphs, the hypergraph is, let's say, a 3 uniform hypergraph is like every hyperedge is a triple of nodes. And you want to find a 4 clique. So you want to find 4 nodes such that all the triples are hyperedges. So it's just a very natural generalization of clique. We don't know how to solve it in sub n to the 4 time. This like matrix multiplication kind of thing fails. And this is there's one of the conjectures I didn't mention says that this you cannot break into the 4. And if you could, then you would get some breakthroughs for you'd get breakthroughs for max sat, and also you would break the minimum weight clique conjecture. So yeah, so like hopefully now you're like informed about why we care about this combinatorial stuff, like why we really want algorithms that are different than Strassen.
Sorry, are these all for we found combinatorial algorithms for triangle finding? These are all implications of that?
Yeah, so okay, no. So let me clarify. So these are all generalizations that, so we want a combinatorial algorithm for triangle detection. But what does that mean? We just want a new algorithm. The point is we want a new algorithm. Why we want a new algorithm? Because we're hoping that it would generalize to one of these. Or it would be simpler, or it would be more practical, whatever. But even any of them would be amazing, right?
And like, if we believe AKSP3 sum and OMV and all these conjectures, wouldn't we believe that we should be able to find a combinatorial algorithm then?
Right, so maybe, okay, if you believe some conjecture, then maybe you don't think you can generalize in all of these ways. But generalizing in one of these ways would already be amazing. So maybe you would refute like this one, or the OMV, or and so on. So, and, but yeah, in refuting conjectures, like it's something we should aim. Like it's not like something to stop us. But okay, but that's really like my point now. Like, people get upset because there's no definition of a combinatorial. And like the point I want to make is that like, okay, you could have defined it based on any of these things. Like you could have defined the combinatorial to be practical or simple or generalizes for weighted or so on. But the point is like there's all these objectives, we care about all of them. And in some sense, there are many definitions. Like each one could be a definition. And they're not necessarily compatible. So you might find an algorithm that generalizes for one setting, but it's not simple, or it doesn't generalize for another setting. And because all of them are great, so we're not working with one definition. We're working with this like loose definition of saying, just anything, like anything but. Like the definition you would hear in papers is like anything but Strassen, or anything that's like cancellation free or something. It's kind of loose, but really like what I'm trying to say is like the reason we're working with this is like we don't care, just give us anything new and we'll be happy. But if you want it to be formal, what I'm suggesting here is just pick one of these definitions and then it's formal. Like say it generalizes to weights or whatever.
Sounds like you really don't want to use any algebra.
No, okay, so it's an important point. Like I'm fine with algebra, right? Some algebraic algorithms, they are fast, or they are practical, or they would generalize in certain ways. So yeah, it's not really like, in some fields, right, they define combinatorial to mean like there's no algebra involved. But we don't want that, right? We're okay with like new, like for example, these algorithms for max flow, these recent developments, they're very algebraic, but we don't know how to use them to break triangle, to find triangle. And if someone does that, we'd be very happy, because then we would.
But then some of the max flow algorithms, people also want to not do that and instead find like more, again, combinatorial is the word.
Right. So I mean, that's the point. There's different motivations for seeking combinatorial. Yeah.
Could you expand a little on one calculation?
Yeah, no. I- like you could say like no subtraction or whatever, but like these are very informal definitions.
Is this like controversial because it like depends on the matrix implementation experts?
I don't think so. Why would it offend them?
Well, because you're saying that you want to do something else. Like,
Oh, I see.
Like all the progress you're making towards n squared, like
I see.
it's fine.
No. I mean, okay, I should have like started by saying like we really, it would be amazing to get n squared with like, I mean, all this progress on omega is really important, and I mean, it's just like for that problem, it's for matrix multiplication, which I mean, it has a million applications, right? These applications in the previous slide, like it doesn't work for them, but there's a million other things for which it does work. So I'm not saying like standard matrix multiplication is not important. Like, of course, it's super important. Just for the conjectures, for the core problems in fine-grained complexity, we want more, basically.
Do you think it's possible that these like Strawson-style improvements have the property that for any constant you can get below that constant, but you can never prove two? Do you think is there any barrier to that being possible?
There is a barrier. You prove that, like, if you could show that,
Yeah.
you will construct like rigid matrices. So kind of the same way you have like tensor barriers, you can show that if such a reduction, if you could show that proving faster than algorithmic algorithms exist, like with better gamma,
Yeah.
then that would, then there was a reduction from say, like an ICT reduction that kind of showed that, like you Bruce had, but that would look like circular bounds and like, or the construction of matrices. So there is a same
Construction
barrier
of
for
what
that.
matrices?
Huh?
Construction of what matrices?
Rigid matrices.
Rigid.
Oh, rigid matrices. Thank you.
So, okay, so what's happening here? So like because of this, motivation for wanting to have these combinatorial algorithms and not having them, right? There's this conjecture that people have in fine-grained complexity, the BMM conjecture, that there's no combinatorial algorithm for a triangle or BMM that's subcubic. And here's the state of the art on that problem. So, okay, so you can do 4 Russians. 4 Russians is what I described yesterday. We break it into like epsilon log n stuff, and you can shave a log squared factor. And then it took like many, many years until there was this improvement to log to the 2 and 1/4. And this was with regularity decompositions. So this is like it's like a math thing. Like you can show that you can take a graph and decompose it into a small number of graphs that are all regular, like random-like graphs. And there's like in math, there's lots of these theorems that do this, like semi-ready regularity decompositions and fancy stuff. So they used one of these, and they shoved a log to the 1/4. They combined it with 4 Russians to do it. And then Timothy Chan shaved the log factor without using any fancy stuff, just like some divide and conquer thing. Like you look at the node, you look at the neighbors, you check their neighbors, and then you remove, like you find the node with the maximum degree or something, you remove the neighbors and you recurse. It's some kind of nice analysis. He shaved log to the log cubed. Watching you improved it to log to the 4 with better analysis. And then last year, with Nick and Kelly, Lovett, and Mecca, we have some new graph decompositions, like kind of like it's again with regularity decompositions, but like more fancy stuff that are more efficient, and we got this super polylog improvement. Okay, but okay, so then like okay, what does it mean to prove these combinatorial lower bounds? So here's an example of a combinatorial lower bound. So you can reduce BMM to triangle detection. This is exactly the same reduction you saw from APSP to negative triangle. If you remove the weights, what you're getting is a reduction from BMM to triangle detection, and it shows that if you solve triangle in subcubic time, you solve BMM in subcubic time. But like it means that you get this combinatorial lower bound. Why? Well, because the reduction itself is combinatorial. So if you could solve triangle with some combinatorial algorithm, you do the reduction and you get a faster algorithm you get a combinatorial algorithm for BMM.
So that says divide and conquer the 15 to the 15 table. So what does that algorithm not do that Strassen does? That's also demanding.
Yeah, but then right, but that just look at the just look at the neighborhoods, and then you remove edges and you recurse. It's like it's not like yeah. I mean, just look. It doesn't really work with numbers, really. It's just like edges.
If we do not have like a precise definition for what a combinatorial is, how do we prove the reduction is combinatorial?
Yeah. So that's what gets people angry, I guess. Also. So the way I think of it is like also in math, right? There's this constructive proof or something. Yeah, someone gives you a constructive proof. It's not well defined what a constructive is. So you can say, I gave you this reduction. I'm telling you it's combinatorial. If you don't think it's combinatorial, fine. But it's kind of like this. Also for algorithms, like you have an algorithm, we say it's combinatorial. But to make it more formal, we could have said like it generalizes in one of the ways that I defined before. Like that's would be one suggestion to formalize things if you wanted. And in fact, like you could ask, do these algorithms generalize in all these ways that I mentioned before? And it's some cases they do, some cases they don't. It's open. Like for example, this one we've been trying to generalize it to like hypergraphs or stuff. It's likely, but we don't know. So I just want to end with like, okay, why it's like so annoying and all this mess with the definition. But let me just tell you the value of these reductions, these combinatorial. I think there's a lot of value in them. So let me give you like an example of a valuable thing that happens. So here's a problem, RNA folding. I'm not going to define it. It's something with DNA. It's like whatever, some folding type of problem. The point is it has an n-cube dynamic programming solution. And you might want to do better, and people have been trying to do better. And well, you could try many things, right? There's 100 new techniques coming every year. There's so many techniques to try to work on this problem. And you could try all of them and work on this problem. Right? But then we showed this lower bound. So we showed a reduction, a combinatorial reduction from cake leak or triangle, one of these combinatorially hard problems. And what it means is that, okay, either you have to, if you believe this conjecture about combinatorial, then you cannot break cubic time unless you use matrix multiplication. So it's like you had 100 techniques to try, but now we're telling you there's only one technique you should try. And that's super useful, and in fact, a year later, the cubic bound was broken for this problem with matrix multiplication. So like, it's really useful for guiding the research. And just to summarize, like what I suggest is this: like you start with triangle, you prove a lower bound for a problem. Then you ask, okay, is this problem really hard, or maybe I can break it with the matrix multiplication? And for a lot of cases, you can. So there's like a subclass that are problems like RNA folding, where you can break them. And then for others, you should try to bring a better lower bound. I mean, you shouldn't stop there. Like if you don't have a subcubic algorithm and you only have a combinatorial lower bound, no, try to get a better lower bound, like maybe with APSP or with this hyperclick thing, which we don't know how to break. Or for dynamic problems, you can use OMV or something.